Let's study Carnot cycle. Now, before analyzing and understanding Carnot cycle, some facts are very important to be understood, which gives us idea about why the Carnot cycle was needed or how it was discovered. The first point about Carnot cycle, which was basis of discovery of this, was, as we already studied, according to second law of thermodynamics, no heat engine can have 100% efficiency. This because always some amount of heat is rejected by a cycle when it is completed. And based on this, in 1824, a cycle was invented or a cycle was developed by Carnot to have maximum efficiency for given conditions. This particular cycle was named as Carnot cycle. And if we talk about this Carnot cycle, another fact about it is, a Carnot cycle is accomplished in 4 steps. The first one is heat absorption by isothermal process. First, we need to write down all the steps and then we'll understand it one by one. Heat absorbed by isothermal process at source temperature, which we can write as T1. The second one is adiabatic expansion. We know that in adiabatic process no heat is involved and the gas is first absorbing heat at source temperature, then it is expanded till its temperature drops to sink temperature T2. That means initially the gas is supplied heat at the source temperature, then it is expanded till its temperature drops to sink temperature. Now the third step is heat rejection, again by isothermal process, which is at sink temperature T2. Because gas was already at T2 due to adiabatic expansion. Now finally the gas is compressed adiabatically, so fourth step is adiabatic compression till its temperature increases to source temperature, which is T1. This is the way how the cycle is completed. It is completed in 4 steps. That's why the engine is called 4-stroke heat engine. Let's discuss these 4 steps one by one in detail along with the indicator diagram of Carnot cycle. Let's discuss indicator diagram and working for a Carnot cycle. Here, as we have discussed that Carnot cycle, there are 4 processes involved. Here you can see the process AB and CD are isothermal processes which lie on isothermal curves. Here we can treat these curves as isotherms, along which these 2 isothermal processes are carried out, and then the process BC and DA are adiabatic processes. Now in this situation we can analyze it in the process AB, which is carried out at the source temperature, which is T1, which can be written as a source temperature at which the gas is expanded isothermally. So in this situation, obviously a heat Q1 is supplied to the working substance, and then From the state B, the system is expanded adiabatically till the temperature changes to T2, which is the sink temperature. So if it is its temperature is changed to sink temperature, it will be in the maximum volume state, and then it is compressed isothermally up to a limit till the volume is decreased up to such an extent so that when it is compressed adiabatically, the initial state can be achieved from state D. Now in this situation, when isothermally the gas is compressed, it will reject some amount of heat, say it is Q2, and it reaches to the state D, and finally adiabatically it is again compressed to the initial state A, and the cycle is completed. In this situation, only two heats are involved, Q1 and Q2, and as processes BC and DA are adiabatic processes, so no heat exchange will take place during adiabatic processes. Here we can easily find out the magnitudes of Q1 and Q2, as these are isothermal processes. Process AB is carried out at source temperature, so its heat can be written as nRT1 ln of VB upon VA. That is the expression we already studied about a heat supplied and isothermal expansion. Similarly, for isothermal compression, the heat will be rejected, but here we can calculate its magnitude as nRT2 ln of, here we'll write Vc by Vd as we are calculating the magnitude. Otherwise, Q2 will write nRT2 ln of final volume by initial volume, which is Vd by Vc. So it will turn out to be a negative quantity. So for magnitude, we have just taken the inverse of logarithmic argument. Now, in this situation, we can easily relate Vb, Va, Vc and Vd as for adiabatic processes. We can simply write between state B and C, we can write T1 into Vb to power gamma minus 1 is equals to T2 into Vc to power gamma minus 1. Similarly, for process D and A, we can write T1 into Va to power gamma minus 1 is equals to T2 into Vd to power gamma minus 1. Now, if these are equation 1 and 2, and if we divide these two equations, you can see by making 1 by 2, we are going to get Vb upon Va is equal to Vc upon Vd. This is also a very useful relation here. And from this expression, we can see here Vb by Va and Vc by Vd are equal. So if these equations are equation 3 and 4, then by dividing these equations 3 by 4, we can see we are going to get Q1 by Q2 magnitude is equal to T1 by T2. So here we can state that heat involved in isothermal process is directly proportional to the temperature in a Carnot cycle. This is again a very important relation which is used in calculation of efficiency for a Carnot cycle. On next sheet, we are going to discuss about the efficiency of a Carnot cycle. Now, if we calculate the efficiency of a Carnot cycle, we know well that efficiency of a cyclic process or efficiency of a heat engine can be given as eta is equals to 1 minus mod of Q2 by Q1, where Q2 is the heat rejected by the system and Q1 is the heat supplied to the cycle. Then we know, as we know, for Carnot cycle, just now we have studied Q2 by Q1 is equal to T2 by T1 in magnitude. So we can simply write efficiency of Carnot cycle can be written as 1 minus T2 by T1. So we can see under a given condition, if we adjust temperatures of source and sink, here T1 is the source temperature from where heat is being supplied, and T2 is the sink temperature, which is generally taken as ambient temperature of surrounding where heat is being rejected. So corresponding to a given value of T2, if we adjust the value of T1, we can maximize the efficiency of the heat engine if we use the Carnot cycle, because this T2 cannot be changed, but T1 can be adjusted for the maximum efficiency of the cycle under given conditions.